Hello, welcome to this video, and in this video we'll be looking at differentiation. Now, differentiation is the process of finding the gradient function of a function. This gradient function is also called the derivative of that function. Let's start off first by looking at the gradient of a curve. Now we know that for a straight line, the gradient is the same at all points and given by the change in y divided by the change in x. However, for a curve, its gradient varies at all points, and the tangent at a particular point is equated to the gradient. The gradient at a particular point on a curve, is equated to the gradient of the tangent to the curve at that point. So if I had a curve here, the gradient at this point would be the gradient of tangent at that point, so the gradient of that line, and the gradient at that point would be the gradient of the tangent, so the gradient of that line. And so if we look at the diagram we have a rod RS that cuts through a curve at 2 points P and Q. Now, if we rotate this rod at point P in this direction, you realize that point Q, which is the second point of intersection of the rod with the curve, keeps coming closer to point P. So you have Q at Q, Q1, Q2, Q3, and Q4, as you can see. Why is this important? You realize that as Q comes closer to P, RS is rotated and be rotated up to a point where it is equivalent to NT, and at that point, Q is at point P exactly. This is important because the gradient of the chord PQ tends to the gradient of the tangent at P as Q moves closer to P, and this will help us determine the gradient of a curve. I'll just say that again. As the rod is rotated, Q moves closer to P, and you can see that the gradient of PQ becomes closer and closer to the gradient of NT, which is the tangent at point P. Let's look at an example. If we consider the function y is equal to x squared, in this case, we given point P the coordinates a squared, since the curve is y is equal to x squared, and we've considered a point Q whose x coordinate is a plus h, and therefore its y coordinate will be a plus h all squared. Now, what do we know? We know that the gradient of PQ, the chord PQ in this case, is given by the change in y divided by the change in x. The change in y in this case is a plus h squared minus a squared. The change in x is a plus h minus a. This should give you 2ah plus h squared out of h, which is simply 2a plus h. This is the gradient of PQ. Now, what did we say? We said that as Q moves closer to P, as Q moves closer to P, the gradient of PQ becomes actually the gradient of the tangent at P. But what happens as Q moves closer to P? As Q moves closer to P, H tends to 0. That's what happens. Because H is the length Mn, you can see that as Q moves closer to P, Mn becomes smaller and smaller. So Q moves closer to P, H tends to 0, and the gradient of PQ becomes the gradient of the tangent at P, tangent to the curve, yeah? And so we can get the gradient of the tangent to the curve at P. How? Because we know that it will be the gradient of PQ when H is 0 exactly. And therefore the gradient of curve at P, I can say of the curve at P, since it's the gradient of the tangent to the curve at P. The gradient of the curve at P is in fact equal to 2a plus 0, which is in fact 2a. But this was, speaking generally. It's not like it was a special, a special number. We just picked a variable a, and so we know that for the curve y is equal to x squared, its gradient function, which we call dy dx, will in fact be equal to 2x. And this is how we get the gradient function of a curve. Okay, we could look at other examples. We could try this for x cubed. You know that we could let our y equal to x cubed, and then what we do is we let delta x to be our h in this case. So we'll let delta x be a small change in x, the small change in x, that causes y to change by delta y. That's what we'll have. And then we know that since what we're setting up really is a point P whose coordinates are x, y, and a point Q whose coordinates are x plus delta x and y plus delta y, with both these points being on the curve y is equal to x cubed. So that would mean that y plus delta y is in fact equal to x plus delta x plus delta x cubed. But what do we want? We want the gradient of the tangent, and the gradient of the tangent is of the chord PQ rather is delta y out of delta x. So that's what we want. So we could take our y to the left hand side, so it'd be x plus delta x cubed minus y. But our y is in fact x cubed. So this is what we have. So you could go with a difference of cubes, or you could decide to expand. I think expanding might be easier. So this is x cubed plus 3x squared delta x plus 3x times delta x squared plus delta x cubed minus x cubed. And that leaves us with delta y being equal to 3x squared delta x plus 3x times delta x squared plus delta x cubed. But what do we want? We want delta y divided by delta x. If you divide the right hand side by delta x, you realize you're left with 3x squared plus 3x delta x plus delta x squared. But what do we know? We know that as q moves closer to p, delta x tends to 0. And as delta x tends to 0, the gradient of the chord pq tends to the gradient of the tangent at p, which is dy dx. And therefore, dy dx will be equal to 3x squared plus 3x times 0 plus 0 squared, which is in fact just 3x squared. And that's the gradient function of x cubed. Okay. We'll look at more examples in the next video.